Hello everyone, welcome back to my channel. And I know it's very long. I think it's been 1 year since I have uploaded any of my video, any of my lectures. I know you all must be a little bit pissed off, but together we are gonna cover some lectures of organic spectroscopy and the remaining one of quantum. I have thought that I'll complete those lectures simultaneously along with organic spectroscopy, since I understand the importance of organic spectroscopy. It's huge, and whenever you attend your exam, or whenever you just know concepts of organic spectroscopy, then I feel it's kind of like free marks. There was a time when I did not know anything about organic spectroscopy, but I learned everything from Anuj sir, from the coaching only. So he taught everything, and I literally became pro. I can say that now because of his help. So finally, I'll be able to teach you all the basic everything. Like, even if you don't know like N of NMR, we're gonna cover that. We're gonna start from the very basic, as if you don't know nothing, and we're gonna cover everything from the examination perspective also, and from the theoretical perspective also. That I can guarantee that you can just find out that what's the structure of particular data. Suppose if I've given you spectral data, and if I tell you to just deduce the structure, then that you can do that easily. So just go with me, follow my lectures, and I'm sure that you'll be able to score marks from this part, at least whatever I'm teaching right now. So without wasting much time, I think the introduction was kind of long, but it was much needed because I wanted to give a little bit personalized touch to you guys with me, since I've been missing for 1 year. So let's go without any ado. I think we should start, and we should learn the very basics through in a very exciting way. So first I'll just pay attention over the screen over here. Yeah, so this is NMR. NMR means nuclear magnetic resonance. So nuclear magnetic resonance means just break this definition into very small part. Like nuclear means nucleus means proton and neutrons. And if I talk about magnetic, it means magnet. So you must be thinking that we are talking about nucleus, then what is the meaning of magnet over here? So guys, whenever suppose any proton, it start rotating in an angular motion, so it becomes magnet. So for any charged species to be magnet, there are two conditions: that it has to be charged first of all, and it has to be in angular position. So when proton will rotate, it will act as small magnet. So that's why we use this term magnetic. And then the third term over here, it's resonance. You can see, I'll just take my pen over here. Yeah, so resonance. So I have told the meaning of this, and now it's resonance. So resonance means when the small magnet over here, so here in this case it's proton. So when we'll keep this small magnet in external magnetic field, I'm so sorry for my bad handwriting. I'm pretty sure that I'll get hold of it gradually along with these video lectures, but bear with me for the moment. So whenever you will keep your small magnet in this external magnetic field, so it will resonate between ground state and excited state. That is the meaning of nuclear magnetic resonance. So that's how you break it, and that's the simplest definition of NMR. Whenever someone will ask you that, okay, you know everything about NMR, but what about the basic definition, that what is the meaning of nuclear over here, what is the meaning of magnetic over here, and these are basic things. And the another basic definition which we have been studying since our undergraduation time, that is whenever EM radiation, that is electromagnetic radiation, it interacts with matter, it's called spectroscopy. So spectroscopy is nothing when any EM radiation come and your matter is here, suppose, right? So it's over here, and when EM radiation strikes over here, so that is called absorption happens and you get signal. So basically you kind of know that what this substance is and how much heat it can retain and certain characteristics associated with this matter. So suppose if you have any unknown compound and you want to know like what is it, so in that case we'll use spectroscopy to know the nature, characteristics and different aspects of this matter. So I hope the basic definition is clear. So let's go over to the further bifurcation of spectroscopy. It is classified further into absorption spectroscopy and emission spectroscopy. So emission spectroscopy is absorption spectroscopy is whenever any nuclei it absorb any EM radiation and then you'll get signal. And in emission, whenever any nuclei it absorb and when it will come back, it will emit some heat or some energy, radiation. So that will be called emission spectroscopy. And I'll tell further differences in absorption and emission. This is very basic definition, that's why I'm going very fast on it. So example of absorption is NMR, IR, UV, rotational, and emission example is fluorescence spectra, charge transfer spectra. And there is one prominent difference between absorption and emission is that in emission, the difference between ground state and excited state, I'm so sorry if I have been mispronouncing that, ground state and excited state, it is very less. It is very less, and here it would be like fine, but here it would be less. So that is the difference between emission and the absorption. And another difference, although on the next slide I've written another differences, but these are very prominent ones which I'm telling you that just hit my mind. So there is one more difference in absorption and emission. In absorption, what happens whenever a matter is there and suppose a radiation is coming over here, suppose I naught. So it will transmit some radiation and then the detector will be placed at 180 degree over here. It will be placed at 180 degree in absorption, but in emission what will happen, suppose any incident light is there, a matter is there, so light will transmit like this. Detector will be over here and light will be transmitted like this. So detector, suppose this is detector, I'm writing it with D. So detector will be placed at 90 degree over here. So remember that in absorption it will be at 180 degree. Detector will be placed at 180 degree with respect to matter, and over here the detector will be placed at 90 degree as compared to the incident light, and same over here. So these are some basic definition that if you want to understand what are the basic introduction of organic spectroscopy. Now coming again to the written part of this differences between absorption spectra and emission spectra. So in absorption spectra, we'll just go through it very fast and then we'll just know the very basics and very important things. Sometimes in examination 2 marks questions are there, and these marks are kind of free, I believe, if you know these things. So just go with me, and in 1 to 1.5 hour we'll be just completing entire basics of this organic spectroscopy, and I'm pretty sure you'll be able to attend questions related to the introduction. Now going back to the topic, it is the absorption spectra. So in absorption spectra, you'll get dark lines or gaps in the spectrum. So suppose your spectrum is like that, you'll be getting dark lines over here or gaps. But in emission spectra, you'll be getting colored lines in the spectrum. Most probably I'll put the picture if I get it to make you guys understand very nicely. And the next difference is that it can be used to figure out the ability of certain objects to retain heat and its absorption level. So absorption spectra tell about any substance ability to retain heat, that how much heat any substance can retain and what is its absorption level. And over here in emission spectra, it is helpful in figuring out the composition of a certain matter. So you will find out, suppose a matter is there and emission spectra is taking place over there. So you will be able to find out the composition of that certain matter, that what that matter is made of and what composition does it possess. And the third difference is that it helps in figuring out the number of substances in the sample. So with the help of absorption spectra, you can find out how many substances are there in any sample. And if I talk about emission spectra on the same side, so the type of photons emitted is helpful in finding out the type of elements the substance is made of, as each element radiates a different amount of energy and has a unique emission level. So basically, you will be able to find out the type of elements a substance is made of. Kind of any substances there, you'll be able to find what type of elements are over there in that substance. Depending on the type of element, suppose in a substance 10 elements are there, so each element will radiate a different amount of energy, and depending on that energy, we'll find out that it will be having unique emission level, and we'll be able to find out that how many elements are there and what type of elements are there depending on their emission levels. So that's all about this basic definition, along with the two differences which I told you guys earlier about the angle, that in absorption it is 180 degree and in emission it is 90 degree, and difference between ground state and excited state. I don't know why I'm saying it electric state. The difference between ground state and excited state, it will be less in emission spectrum, and in absorption it will be more. So now that part is over. Now we are heading to a little bit important part. Those are conditions, and those are different aspects of any spectroscopy. So these conditions should be satisfied when it comes to the spectroscopy, organic spectroscopy part. So the first condition is that Bohr frequency condition. That means frequency of EM. EM means electromagnetic radiation. Frequency of EM should be equal to energy gap between energy level. This is necessary condition. So first of all, let me just go back to this first slide, and let me guys ask you that these are energy levels. So whenever we talk about spectroscopy, we always talk about energy levels. So you must be thinking that, okay Komal, these energy levels, like, we can't just imagine it, we can't just feel it, like why they are there whenever we talk about spectroscopy. So well, my answer would be that whenever there is a motion, like there is motion in any matter, so due to motion, what will happen, energy levels are created. Motion in matter, oh my god, my handwriting, it's worst in the world, I feel. Motion in matter, I will try to write it in a good way. So motion in matter, so due to which energy levels will be created like this, and what will happen now, that the energy gap between these energy levels, so whenever we'll put any electromagnetic radiation, that should be equal, its energy should be equal to this energy gap, then only it will give a signal, otherwise it won't be possible. And same is the condition over here. Bohr frequency condition is same, that the frequency of EM, that the frequency of electromagnetic radiation should be equal to energy gap between energy levels, energy gap between these, I'm talking about these. So this should be equal to this frequency of EM, and this energy, like you'll be talking about this energy and this is frequency. So this energy can also be written in terms of frequency like this. E is equal to h nu, you can write it nu is equal to E by h. So here it should be equal to this energy gap over here. If I talk about del E like this. Yeah, so this, whatever this energy gap will be, that should be equal to the frequency of incident electromagnetic radiation. That is must for getting any signal in spectroscopy. So that is the first condition, that is very important condition. I hope you got the point. And also I told you in the first slide that motion is there, motion in matter is there. Yeah, I told you. So you'll be telling Komal, okay, why is there any motion in matter? I'm pretty sure that you will be very much afraid to ask me in person, but since it is an online class, I can tell you like that and you won't be punished, right? So jokes apart, so motion in matter is why does it happen? So basically it happens because there is change of spin of electron in matter. So due to that, motion happens, and due to motion, energy levels are created. And when we put frequency equal to this gap, excited state, ground state difference energy, we'll get the difference over here. So we'll put radiation frequency equal to this, and then only we'll be able to get any signal. That is the basic definition. I hope guys you got it, that the meaning is that change of spin of electron will happen, motion will happen, energy levels will be created, and rest is history now. Fine. That is the first condition, that is Bohr frequency condition. So now coming to the second condition, that is selection rule. So selection rule, it's very important guys, it's very important. That is, if I not equal, you must have seen it like thousands of times, I'm pretty sure, but let's just go with it, go with the flow, because otherwise things will not be completed and it will not be considered full. So if I is not equal to 0, so that then the nuclei will be NMR active. So guys, nuclei, suppose a nuclei is there, fine, and this I is nuclear spin number. I is nuclear spin number. So if it's any nucleus I is not equal to 0, then NMR will be active. So it can be 1, it can be 1 by 2, it can be 2, it can be 3 by 2, blah blah blah. So in that case NMR will be active. And if it's any nucleus spin number is 0, then NMR will be inactive. That is the first condition. So if I not equal to 0, we'll head to next thing. So if I is equal to half, then that nuclei is called non-quadrupolar nuclei. So some examples are 1H, 13C, 19F, 31P, 15N, like that. And another one is if I is greater than half, then that nuclei is called quadrupolar nuclei. I'll tell the difference in these two things later on in the later lecture. So for now, just go with it and just understand, okay, I is equal to half, and some examples are over here, fine. And I greater than half, and some examples are over here: 2D, 14N, 10B, 11B, 27 aluminium, chlorine, bromine. These are some example of when I is greater than half. So another like the very basic shortcut is how do we understand that if some nuclei is NMR active or not. Suppose we'll see proton and neutron, fine, we'll just focus on that, and then we'll deduce if I is not equal to 0, then we'll consider it NMR active, and if I is equal to 0, then we'll consider it NMR inactive. If proton and neutron are even, then consider that nuclei inactive, straight inactive. If both are even, if any of proton or neutron is odd, you can see if proton is odd, neutron is even, or if proton is even or neutron is odd, then I will not be equal to 0 and NMR will be active. It would be NMR active, not NMR will be active. I take my words back. So that nuclei will be NMR active. And if both proton and neutron are odd, then again it will be NMR active and it will not be equal to 0. So basically any of them should be odd or both of them should be odd in order for the nuclei to be NMR active. And if both are even, then the spin will be 0, and then spin number will be 0, and then the nuclei will be NMR inactive. Just by heart this statement that proton, neutron both are even, then it will be NMR inactive. And another you can see another shortcut is there. If the mass over here, Suppose atomic mass is over there. So this molecular weight is there. So if we'll just divide it by 4, if it get divisible by 4, then it will be NMR inactive. So suppose it is over 16. So 16 divided by 4, that is 4. So that would be NMR inactive. 12 is also divisible by 4. Over here, 23 is not divisible by 4. So that would be NMR active. Fine, I told you that if it is divided by 4, that will be straight inactive. Straight inactive. Over here again it is 13, it is also active. Fine. And some people, I know some lot of people, they don't know that how do we calculate neutron also. No worries, I'm here to teach. And if you never got the opportunity to learn, so I'm here to teach you, and I'll tell you the very basics as I promised initially. So suppose I take this example, 23 sodium 11. Fine. So this atomic number is always proton. Consider that proton is always equal to atomic number, and neutron will be always equal to whatever would be weight, atomic weight, minus this atomic number. Just minus them and you'll get the neutron. Fine. So that would be like, that's how you calculate proton and neutron. Very basic thing. I know you all must be pissed off that why are you teaching all of this, but understand, some students are there who do not know such basics, and I'm here to teach. So these are some basic things, and I think we just got done with this selection rule. And also this is something a little bit mathematical selection rule, but there is this theoretical selection rule also, the way you must have learned in this spectroscope, physical spectroscopy, like in IR, like in rotational, you should have permanent dipole moment, like in HF, HCl, HI, CHCl3. Like in IR, you should have dynamic dipole moment. Fine. Dynamic dipole moment. And in this Raman, you should have this changing dipole moment again. So and mathematically also in Raman, the J is equal to plus minus 2, vibrational quantum number is plus minus 1, and in IR vibrational number is plus minus 1. These all things you'll understand more in these in physical spectroscopy. You'll understand there only. So now coming to the third aspect of spectroscopy, that is Boltzmann population ratio. You all must be aware of it, I'm pretty sure, but let's revise it again. That more population in ground state, more intense the signal will be. So these are energy levels, and if there is more population over here, then more the population over here is, the intenser the signal will be over here. And there is one more formula associated to it, that is Nj by Ni. Like J means that is excited state, and Gj means this degeneracy by Gi, e raised to power minus e raised to power excited state minus E ground state divided by K, this Boltzmann constant, this is temperature. So always remember condition like this, always remember this formula, that J will be over here, I will be, that means excited state will be in numerator, and this ground state will be in denominator. Same over here, Gj by Gi. J means excited state over here, just remember. And e raised to power minus, we always write del E, right? So del E will be E excited minus E. There are many forms of this there are many forms of this formula, but always stick to it in my just case. That would be easy for you guys, because what will happen that you'll get a lot of people get confused, and just by the minus difference and by just putting these things over here, like they just forgot to put minus, and they just put this ground state over here, excited state over here, and you just messed it up. So just always remember that, always write it in this form. This is the simplest and the easiest form, that is Nj by Ni. excited, ground state, excited state, ground state, excited state, ground state. Just put this, that is the formula, and just Gj by Gi e raised to power, you can put it like minus del E by kt. So guys, we can just deduce some interpretation from this formula, that is like suppose is there any, if you can see from here this formula, that the population in ground state has some relevance to temperature, the population in ground state has some relevance to energy difference. So let's see how they are associated, and in examination there can be a question that suppose if there are more population in ground state, so what will happen, that if temperature will increase. Fine, so will it increase or decrease? Like over here, the ground state population, it will increase or decrease with rise in temperature or with energy difference. What will happen, that if I just increase the difference, then what will happen to the nuclei present in ground state? These all questions can be asked. So guys, so Ni, so this number of molecules present in this ground state. So if I just increase this from this formula, we'll just understand from mathematical purpose over here, that if I just increase Ni over here, so what will happen to this entire quantity? It will decrease, right? It will decrease. Yeah, it will decrease for sure. Yeah, because what happens that because this number will increase in denominator, so the entire unit, it will decrease. So this entire unit will decrease. So this will decrease. So what will happen? This whole thing, it will also decrease. This will decrease. So that means what will happen? That this will decrease. So this means that this number must be more. This number must be more because there is negative. Suppose there is decrease. So that means the number should be more over here. So because in minus 4 is larger or minus 2 is larger? Tell me. Minus 2 is larger. Fine. So to decrease this number, I have to increase the power over here because this is less number. This is less in number. Fine. So if I have to just decrease it, what will I do? Just leave the minus over. I'll increase the number over here so that this entire quantity, it just decrease, because over here it just decreased. So over here it should also decrease. So to decrease it, what should I do? I should increase this number over here so that whenever increased number comes in front of minus, so that will become small. Whenever increased number comes in front of minus, it becomes small automatically. I hope this is a very basic concept and you understand. So this will become small. Fine. Yeah, so this number, just keep entire things over here. So if you just increase this number, yeah, you will increase this number. So what will happen? If you increase this number, this temperature should decrease. Fine. Overall, then only it will happen. Let's just go in a reverse manner. To understand it nicely. Let's just repeat it. If you know all these things, just skip the part and go to the next part. Yeah, suppose if I just decrease this temperature, what will happen? This entire quantity, this part, imagine, if I just decrease this temperature, this will increase del E. If del E will increase, that means number got increased. If number got increased in front of minus, that number automatically becomes small. If you don't know, you should know it now. That if a number get increased in front of minus, it becomes small. Like the scale, you know it. Very basic. That if number keeps on increasing over here in minus side, it will keep on decreasing. So that's what is happening. If number will increase over here in front of minus, it will automatically decrease. So decreased number multiplied by something, that will be decreased only. Fine. So it will be decreased quantity and it will be decreased whole number. This Nj by Ni, this will be decreased. So Nj, it is decreased. So if numerator is decreased, to balance it out, numerator will increase. So that means I started with temperature decreased, temperature just decreased, and my Ni, number of particles in this ground state, it increased. And same with del E, you can see over del E, when I just increase, if I just increase this number, same thing with temperature I did, and if temperature decrease, del E increase, this increased, so entire quantity in front of minus decreased, this decreased, Nj decreased, and Ni increased. Just if you are finding some trouble over here, just leave the comment or just ask me in the Telegram group. You are more than welcome to ask questions over there. So yeah, so what will happen now with the increase in Ni, there is increase in del E. So that means if there is more population in ground state, this difference will be more. Always remember. And if there is more population in ground state, what will happen? Temperature should be less. That is the condition, and that is the Boltzmann population ratio. That is the interpretation from here. I hope that is clear, and I try to make it as easy as possible. And let's see. Let's just go to the next slide. Yeah, so guys, now coming to the other aspects, that is how to calculate energy levels. The formula is very simple, that is 2I plus 1. Suppose your spin number is half, so the energy levels, EL means energy levels would be 2 into half. So it got just cut, 1 plus 1, 2. So my energy, 2 means my energy levels will be 2. Having spin this, whenever spin is half, so you'll always keep it plus half and minus half. Same, you call it Mi would be this. If it is half, suppose if it would have been 1, I is equal to 1, then it would be ranging from plus 1 to minus 1. That is plus 1, 0, minus 1, like that. It would be having 3 energy levels. You can put it in formula, that is 2 into 1 plus 1, that would be 3, and those 3 will be denoted like this, plus 1, 0, minus 1, like the way it has been represented over here, plus half and minus half. Fine. So over here, this is nuclear spin number, and nuclear spin angular momentum, there is another term related to it, that's a nuclear spin angular momentum, that the formula is under root I into I plus 1 h by 2 pi. That is the formula. And this is mu p, that is magnetic moment of this proton. That would be, there is one formula, you should know it, that is GNE. The N is in this subscript E I by 2m. Always remember 2m as tum. I always remember it like this, tum. So the formula is G, basically N, related to the atom, E, I, this angular momentum, nuclear spin angular momentum divided by 2m. This is the formula. So sometimes it is very important to understand this all things. Now I'm starting to take things little bit mathematically. So just pay attention over it. And you all must be thinking that what is Gn over here, Komal? So basically this G is physical constant, and it is different for different atom. So I remember for hydrogen it is 5.6, and it basically tells that how easily, so the significance of G over here, of this physical constant, anyone can ask you in this Viva. So just listen to me carefully, that the physical significance of this G, this physical constant, is basically when it tells that how much a proton can rotate easily in any nuclei, that how easily a proton can rotate in any nuclei. So it is the physical significance. And there is some things you should know, that what happens to this formula when external magnetic field is absent. When there is no magnetic field, it would be Gn same, E by 2m same, and this I, yeah, so that would be under root I plus 1 h by 2 pi. But when magnetic field is there, when magnetic field is present, that means B is not equal to 0. So in that case, what will happen? It will be segregated like this, and it will be having formula like this, Gn E by 2m. So instead of this, you will be writing half. If it is for plus half, it would be h by plus half h by 2 5, and if it is for minus half, gn e by 2m minus half h by 2 5. So this in case of when Bz is there. Bz means external magnetic field is there. When no Bz is there, you will write it in terms of angular momentum. So these are some mathematical thing which you should know, and we'll just try to find out that some basic formulas. Sometimes question comes in our examination based on that. So guys, going to the next slide. So if any Bz is applied, that means if any external field is applied, so that formula becomes, the energy becomes, that becomes this magnetic moment into this external magnetic field strength basically. So this magnetic moment always used to measure the strength of any magnet. You should know that. So what will happen when B is 0? It is over here. When B is not equal to 0, like in this case, so this becomes the formula I told you. E excited will become what? E excited would be minus U, like E. If I talk about I plus half, remember I told you plus half was there over here and minus half was over there. So plus half you will put it. So what will happen? Minus mu. Mu was there, that the formula was Gn E by 2m half h by 2 pi into this for ground state, I'm sorry, yeah, ground state, into B, external field. Fine. So it would, you can write it like this now, minus, so this minus half Gn E by 2m h by 2 pi into B. Always remember this is plus half, but if energy related to it, that would be minus half, and this formula. Same over here, when you'll put minus over here in excited state, you'll put this Gn E by 2m minus half h by 2 pi into B. So this minus will become positive and it will become positive. You can see over here. So always remember it is plus half minus half, this spin, but in energy this sign will change. So never thought that minus half is there, so you will write minus half over here. Fine. So there is another thing written over here, that is jitna energy gap hoga utna hi radiation dalni hogi. So basically depending on the gap we'll put radiation. Fine. I told you that the frequency of EM radiation should be equal to this gap, that means this del E. So when you will subtract this quantity from this, so that gap should be equal to the frequency of EM radiation. Fine. So let's just go to the next slide. Yeah, that's what I have done over here. So this is, yeah, so when you'll take the difference, so del E means E excited state minus E ground state. E excited state, I told you it would become positive and the ground state would become negative, and this is minus. So half minus will become plus. So half plus half would be 1 and remaining things would be same. So del E also equal to h nu, you know that. So when you'll just put this equal to this, so what will happen, this h and h will cut out and this term entirely will be called this gamma, and this gamma is called gyromagnetic ratio. So guys, you must have seen this formula, and that's how we deduce this formula. You should know it. And I knew that there is no benefit of telling you if you are just preparing it for exam, but you should know it. Then only you will understand the essence of any subject. So suppose over here, like if I tell you directly, you won't be knowing it. Now you can tell like how this formula is coming, how plus half is over here, how minus half is there, and like that you can tell. Fine. So these all things are important, otherwise you can skip it. As I told you, it would be introduction, and from the next lecture or next to next lecture, we'll just start practicing questions basis, like some practical question. We'll be covering number of signals and how splitting and the chemical shift values, and everything will be coupling constant, everything will be covering this heteronuclear NMR, and this mass IR UV will be covering everything. So just trust me, and we'll just cover everything and you'll be knowing everything. So this got cut, yeah. So this nu would be equal to gamma b by 2 pi. So you must have seen that I have put this like this tail very long. So for now, just remember that with nu I have put this tail little bit long. I'll tell you the reason later on that why I have told you the difference over here, that with nu I have written this little bit tail long. Like you can write it like this also, but there will be one more thing where you will be confused. So I have written little bit long. Otherwise this is same only. Just to make the difference, guys, just nothing more. I have written along this just to tell you something later on. That's it. Otherwise it is same only. Gamma. It is gamma only. You guys remember gamma, otherwise you will be confused. Yeah. So it is gamma b by 2 pi. Fine. And this B is external magnetic field. So remember this formula. This formula is very important. I can't tell you. I guess there was one question from this in my time when I was appearing for exam, and I've seen couple of questions coming again and again in the exam from this part. So I think you should just learn this formula, and there is a little bit twist to this question also. I'll tell you in the coming slides that what can be the twist and how can the examination play with the question. So this gamma is equal to and this gamma is also equal to this. So then there you have two formula. Gamma is also equal to this 2 pi nu by b, and gamma is also equal to this physical constant E by 2m, this physical constant. Fine. So this is the basic formula. This is very important, guys, very important. Please just don't forget this question. Always remember, frequency is gyromagnetic into this gyromagnetic ratio into this magnetic field. Always remember. Always remember, guys. So guys, I told you in the last slide that gamma is equal to this this nu is equal to gamma b by 2 pi. Fine. But if you just multiply it, it become 2 pi nu is equal to gamma b. So gamma b become equal to this precessional frequency. Precessional frequency, guys, is called precessional frequency. Fine. Yeah. So this gamma has another formula, that omega by b is equal to 2 pi nu by b. Now the question comes from where? So you can see over here, I wrote over here that is 2 pi nu by b. So if I take units, examiner always try to play with units over here. So what does he or she do? That if I take the unit of gamma over here, what it will become? This pi. So I'll put radian. Yeah. Frequency, this unit is per second. Tesla is in denominator. So when it will come in numerator, it will be this per Tesla. So the unit of gamma is, whenever you write it in terms of this omega, it is radian per second per Tesla. Fine. So what will happen? Also, there is one more thing, that gamma is this is gyromagnetic ratio. It is physical constant again, means everywhere it will remain same, but it is different for different atoms. So it does not happen that where it is. So it will be same, but it will be different for different atom, just like the way I have written over here. For one, like this, for hydrogen, the value of gamma is this 267.513. These values are very necessary. You should know what are these values. You should learn these values. They will help you. There are only 4 values basically. General one, that are mostly used. So in the next slide you will be seeing the remaining 3, but for now just bear with me. So this is 267.513 into 10 raised to power 6 radian per second per Tesla. So whenever this unit is there, radian per second per Tesla, that is always happens in case of this precisional frequency. Always remember that. Yeah, going to the next slide. Yeah, so I told you for this 13C, it is gyromagnetic ratio value is 67.6 into 10 raised to power 6 radian per second per Tesla. For fluorine, gyromagnetic value is 251.7 into 10 raised to power 6 radian per second per Tesla. And for phosphorus, gyromagnetic ratio is 108.29 into 10 raised to power 6 radian per second per Tesla. Fine. So these values are in terms of omega. Fine. That is in term of omega. So what if I want a value in terms of frequency? So what will happen? So if I want value of frequency, what will happen? So omega is 2 pi nu is equal to gamma b. So nu would be gamma b by 2 pi. Fine. Nu would be gamma b by 2 pi. So what I'll do that I'll divide these values by 2 pi. So I'll get the frequency. You know omega is gamma b. Fine. So if I just divide the value of gamma b, that is omega only, divided by 2 pi, I'll get frequency. Fine. I'll get nu. So that's what I'll do over here. Just guys, just pay attention. I'll tell you very important thing over here. An examiner always plays with this thing. Always. So just pay attention over here. If I divide this value, remember gyromagnetic value was this, gyromagnetic ratio 267.5 into 10 raised to power 6 per second per Tesla, radian also. Yeah, radian per second per Tesla. And this is hydrogen. For hydrogen, the value was this. So, but if I divide it by 2 pi, I'll get the frequency. It in terms of frequency. Fine. Yeah, I'll get the frequency. Yeah, I'll get it in terms of frequency. So nu. So what will happen now if I just divide it by 2 pi? So what will happen? It would be 42.6 into 10 raised to power 6. Radian will cancel out like the unit only. Per second per Tesla. So per second can be written as hertz. And it is 10 raised to power 6 hertz. So we know that 1 megahertz is equal to 10 raised to power 6 hertz. Fine. So 10 raised to power 6 hertz can be written as megahertz per Tesla. Everywhere these units are there. Everywhere these units of gyromagnetic ratio is used. So what examiner does, that people, what they do, that suppose if examiner has given some 50 value, suppose if he has given megahertz per Tesla. So he has asked you to find the frequency. So you must be worrying that what frequency do I need to find out, whether it is precisional one or this one. So what will happen? Just check the unit of gyromagnetic ratio. If it is megahertz per Tesla, per second Tesla, like that, always this nu you have to find out. Then the formula would be nu is equal to gamma b by 2 pi. Fine. But if this gyromagnetic ratio, it's very important guys, very important. Just listen. If the unit has been given, suppose if he or she has given units in terms of 150 into 10 raised to power 6 radian per second per Tesla, like this. So if the units are in terms of radian, always you will find this precisional frequency first, like this, gamma b, and then if so that's how you'll find it. Fine. That is the thing. Just always, examiner will always try to play with thing. Always remember radian means related to something omega, and with this related something frequency. Just see what units are examiner is asking, what units are asked, and all these things. Always remember this, very important. Examiner always plays with this question if they want to test your basic knowledge. So that is the thing. So there is one more thing over here. So that suppose there is one deduction. If you say that nu is equal to this gamma into b. Fine, gamma in terms of this, yeah, this is gamma into B. So B is equal to, suppose 1 Tesla is there, so nu would be, this gamma is already divided by 2 pi over here. Can you see it is 42.6? For hydrogen it is there. Fine. So you must be thinking that, okay Komal, you told us that it is gamma B by 2 pi. Yeah, but over here it is already divided and written 42.6. Fine. Over here you can see they did not write this, where is the, yeah, they did not write 267.513. They just directly wrote 267.5 divided by 2 pi. So they already considered it. That's why I just put the long gamma over there to just segregate that this is divided, this long gamma is gamma basically divided by 2 pi, just to segregate. But you remove the confusion and just play with these things like that only. So it is 42.6 megahertz per Tesla into, suppose B 1 Tesla. So my frequency would be 42.6 megahertz. So that means the difference, if there is 1 Tesla, like there is a magnetic field of 1 Tesla is applied, so this difference is there, energy difference is 42.6 megahertz. So suppose there is 2 Tesla, what will happen, that 42.6 megahertz into 2, because the formula is this into B. Fine. Whenever I read this, always consider, like with the long tail, always consider that it is automatically divided by 2 pi. Fine. That was my motive earlier, to write this tail so long. So this nu is equal to 42.6 into 2, that would be 85.2. Now the difference will be more. Fine. So the difference can be increased by increasing this what do you call, magnetic strength. So you can see here population is more, and signal will come very in less time. In less time only signal will come if the difference is more over here. So that's the beauty of increasing the magnetic field. Same thing I guess written over here, but we'll just repeat it, that omega is equal to gamma into B. So energy gap can be increased. Just now we saw that energy gap can be increased by increase in magnetic field, like just in last slide. See, energy gap, it just got increased over here. It just got increased over here by increase in magnetic field, right? Yeah. So yeah, so energy gap can be increased by increasing magnetic field. So over here, if B increase, this omega increase, that means frequency increase. Frequency increase, it means frequency of outside radiation. That means it will also increase, and number of transition will increase, and we'll get good signals. So basically, if we have more magnetic field, so that would be helpful in getting good signals, that will be helpful in getting transitions more. So I hope that is clear. So that is the very basic thing to understand. Now we'll be jumping to this TMS. There is one more thing which we discuss about, that we always there's questions in examination that why TMS is a reference standard. So though I'll be explaining it technically in later lectures when you will be understanding the concept of this upfill, downfill, shielding, deshielding, but for now just understand that this TMS is tetramethylsilane. SiCH3CH3CH3CH3. Fine. So basically, why do we use it as a standard whenever we measure whenever we measure NMR spectroscopy of any compound? Why do we use it as reference? Because what happens that it is inert. First of all, it does not react. Second is we get sharp signal because all these hydrogens are, these are 12 hydrogen, and they give very sharp signal that we can identify, and that we can take as, okay, now this is 0 ppm. Like that only, ppm is the, like that's how we just measure chemical shift. So this is chemical shift value. We'll be discussing that also in the upcoming lectures, but for now, bear with me. So this, you'll get very sharp signal, and you'll be able to find out, okay, this is the signal of this tetramethylsilane, and then you can just compare things. So in that way, it will be easy. It is volatile, so it can be evaporated. It won't be reacting with this. other original mixture, so you don't have to separate it out after putting it. And also this silicon, it has very low electronegativity. So what will happen, it has low electronegativity, so what will happen, it will shield these protons, hydrogens, it will shield these protons, due to which we'll get a signal in upfield region. I'm sure that you did not understand this thing, but this thing I'll teach you guys in coming 2 to 3 lectures, when I'll be talking about de-shielding and upshielding. There will be talking everything, that what happens, why less electronegativity is causing more shielding of hydrogens over here, and why we are getting signal at 0 or like at such a low value, and like that. Fine. So we'll be discussing that later on, but for now, just understand that silicon shield these hydrogen very much, due to which we get a signal at very upfield region. This is called upfield region, and over here around this 10 ppm like that, it is called downfield region. Like the way you go over here, this is downfield and this is upfield. And there is one drawback, that TMS, it can't be used in H2 or D2 in aqueous solution. So in that case, we have to use DSS. DSS is it was something like this. Structure was this, like this. Yes, CH2. Yeah, this is sodium salt of trimethyl silane propane sulfonate. Propane sulfonate. So that is the name of this. You can Google it out also, you'll get the same most probably, but that just I tried to find out by the structure. But this is the structure, this is the definite structure. You can find out the real name, but the name would also be same 99%. Okay, so now going to the next. So what does it mean that okay, so guys, there is one more thing, that whenever we talk about that this instrument is 100 megahertz, you must have heard that this NMR instrument is 100 megahertz, this is 200 megahertz, this is 400 megahertz. So what does that mean? We don't know exactly what does that mean, Komal. So can you please explain it? Yeah, I'll do that happily. That's what I'm doing over here. So what happens that any nuclei, if that is kept in, suppose in 2.4 Tesla in that magnetic field, fine, and the energy difference, that is 100 megahertz. So what happened? So suppose if I have taken this TMS hydrogens also, they are placed in 2.4 Tesla and they are rotating with this frequency. Fine. So what will happen? We'll use radiation. I told you, whatever the difference would be, we have to use the radiation of same level. So we'll use radiation of 100 megahertz only to excite the proton from ground state to excited state to get a signal. So this I have been repeating since the start of this lecture. So the instrument will be called according to the frequency of the proton is rotating. Proton is rotating with 100 megahertz. Okay, the instrument will be called 100 megahertz, and obviously the incident radiation will also be same frequency. So you can say the proton frequency or the incident radiation, same frequency will be there, so the name would be according to that only, 100 megahertz. Suppose a TMS hydrogen is placed, like I've written same interpretation with this. So suppose if TMS hydrogens are there, they are placed in this 4.8 Tesla magnetic field and they are rotating with this 200 megahertz. Suppose a proton TMS hydrogens are there, they are placed in this magnetic field strength and they are rotating with this frequency 200 megahertz, like this they are rotating. Fine. So we have to use radiation of 200 megahertz only to get a signal, to get the proton excited from ground state to excited state, to get a signal. Fine. So that instrument will be called, now what it will be called, you tell me. Here it will be called, it was called 100 megahertz and here it will be called 200 megahertz. So whatever the difference will be and whatever the proton is rotating with the frequency, that will be used as the naming pattern, naming pattern for that instrument. Over here it was 100 megahertz, over here it's 200 megahertz. This is very simple numerology which I wanted you to understand. Mnemonics basically. Yeah. Now coming to sensitivity, there is also a term called sensitivity when we talk about this spectroscopy. So sensitivity means sensitive always considered as a negative term, but it's not negative that if hydrogen is sensitive that means it's bad. Hydrogen should be sensitive. If I talk about NMR, H1 NMR, then it should be sensitive. That means that nuclei, sensitive means nuclei is showing highly intense signal at low magnetic field. That means this hydrogen nuclei, this will show highly intense signal merely at low magnetic field. That only I need, that I need very small magnetic field, and if I get very sharp signal, that means I'll call that nuclei as sensitive. And let me tell you, my friends, hydrogen is sensitive. It just get signal. I'll tell you the reason also. Just hold on. Let me just rub this thing. Yeah. So this is gamma. It depends on two factors basically. First is this gamma, that is gyromagnetic ratio. Gyromagnetic ratio, it depends on population ratio. Remember that. So if gamma increase, gyromagnetic ratio increase, so a nuclei, that means our nuclei can rotate fast at low magnetic field. That is the definition of sensitivity. So one hydrogen is highly sensitive. So gamma increase, so since gamma increase, sensitivity increase. And we know that gamma of hydrogen is 42.6 megahertz per Tesla. And that is more, you can see that is more as compared to the other quantities like C, 13C, this 19F, 31P. Fine. So hydrogen is sensitive because they have more population in ground state, more transition, more intense the signal would be. Because in hydrogen what happened, more population is there in ground state. You will get the reason also why there is more population in ground state, that the relation is with abundance. So there is more population in ground state, so more transition will be there in case of hydrogen, so more intense will be the signal. So at very low magnetic field you can get very intense signal, and gamma increase, so sensitivity is also increasing over here. That is the moral of this gyromagnetic part. Remember that. Fine. So let's go with the next slide. So the second factor which aids in increasing the sensitivity, that is natural abundance. So before talking about natural abundance, I want to give you one very small tip, that how do you decide molecular weight mathematically. So you must have seen that there are two isotopes of this chlorine. So you never say that, okay, the atomic weight is 35 or 37, what is the molecular weight? So what do? We take natural abundance in account. So it is 75% and it is 25%. It is known. It will be given, or you will be knowing that the 35Cl is 75% abundant on Earth and it is 25%. So what will happen? We will just find out its value like this, that molecular weight we'll find out. Suppose if I take a slice, so this will be considered one part, this will be considered 3 part. Fine. So there will be 3 molecules because it is 75%. 75% makes third 3/4. 25% is 1/4. So it makes 3 molecules out of 4 and it is 1 molecule out of 4. So what will happen? 3 molecules are there of this atomic weight. So I'll multiply this, and 1 molecule is there with this atomic weight 37, and total how many molecules are there? 4. So I'll just multiply it, sum it, divide it, and then I'll get this. So that's how you get the molecular weight. That is an additional tip. Thank me later. Just kidding. So there is natural abundance. I was talking about natural abundance. Let's go to that. So natural abundance of this hydrogen is 99.7%. I've written over here. This is very important, guys. You should know all these abundance. Just learn them. It's very important. You'll you'll find them very effective when you will be doing this mass spectrometry. So in deuterium it is 0.3%, and this also 0.3%, and sources are sea and ocean. And in terms of 13C, you'll see 13C is 1.1% abundant, 12C is 98.9% abundant, 14C is 0.014% abundant, and 19F has no isotope, so 19F has 100% abundancy, and 31P, it again is 100% natural abundant. So just learn this value and they will be very helpful, let me tell you that. So let's go to the deduction that how natural abundance is increasing the sensitivity. Fine, how it is increasing the sensitivity? So let's understand. 12.6, this carbon isotope of 12, it is spin is 0 over here because it's divided by 4. Fine, so spin will be 0. But 13 and 6, it will be having spin I is equal to half. So suppose if I have 100 molecules of CH4, fine, so what will happen? Among 100, 99% 12C, like that would be 12CH4, that would be inactive, because our 12C, you can see that is almost 99% abundant. You can see over here 12C is almost 99% abundant, and 13C is only 1%. So that means 1% of 100 molecules will be active. So 1% of 100 molecules, 1% of 100 molecules will be 100 only, sorry, 1 only. Fine, so that would be 1, and over here 99% of 100, that would be 99, so that would be inactive, and it would be 1 will be active only. So that means I took 100 and only 1 is coming active, so only 1 will be giving signal. So you can just understand. But if we talk about hydrogen's abundance, just see in this slide what will happen. In hydrogen, suppose if I have 100 hydrogen and their abundance is almost 99.7%. Can you see? In above slide also you can see that is 99.7%. That means almost 100% 1H is found on this planet. So what happens that almost all are active. So lot of particles will be there, lot of nuclei will be there, which will be in ground state, and lot of transitions will be there, so that means intensity will increase. So that means our sensitivity, it got increased with natural abundance. As natural abundance increased, sensitivity increased. 13C is not sensitive, but 1H is definitely sensitive because its natural abundance is so much that we are getting so high signal. Fine, so this ground state population increased. That's what I've written. Number of transition increase, signal intensity increase. So if I just take the moral of both the thing of gyromagnetic ratio and natural abundance, so if I just combine them on the basis of this gamma, gyromagnetic, 13C sensitivity is 1/4 of 1H sensitivity. How come? See, 1H is this 42.6 value. Fine, 13C value is 10.7. Remember in that slide I told you. So it is almost 1/4. So we can say that 13C is 1/4 of this 1H. Sensitivity, guys. Always remember sensitivity. Fine, in terms of gamma. But in terms of natural abundance, it is something else. You can see 1H natural abundance is almost 100%. 13C, it is 1%. So that means it is 100th. 13C sensitivity is 100th of 1H sensitivity. Over here in terms of gamma, it is 1/4 only. Over here in terms of natural abundance, you can see it is 100th. So if I just combine both of them, what will happen? If I combine both of them, so overall if I talk about this, so overall 13C sensitivity, overall I'm writing over here, overall it would be 1/4 of this and 1/100 of this. So of 1H sensitivity, that means 1/400 of 1H. That is 13C sensitivity. Yes guys, that 13C is 1/400 times of 1H. So it's very less, and we can just have one deduction over here also. Suppose if we get signal in 15 second 1H, but in 13C we'll get signal in 4 times more. Fine. And now the question is that, okay, we are getting a signal very late in 13C. What happens that the question now the question is 13 signal, it will take time. So can we increase the sensitivity of 13C also so that we'll get signal in less time? Well, the answer is yes, you can increase the sensitivity of 13C. Let's see how to increase the sensitivity. So you would be saying, yes, Komal, the factors are gamma and factors are natural abundance. So let's see if we can play with gamma or natural abundance of 13C so that sensitivity increases. Fine. So the first factor becomes this gamma. So you will see that for one hydrogen, this is 42.6 megahertz, and for 13C at 1 Tesla it is 10.7 megahertz. Fine. But guys, tell me first, you will increase sensitivity by increasing gamma? No, that is not possible. How can you increase gamma? Because gamma is physical constant. It is constant, though it is different for different atoms. Like for hydrogen it is different, for carbon it is different. But you can't increase it, fine? So what can you increase? You can increase the magnetic strength. So if you will increase the magnetic strength, this difference will automatically increase. Remember that thing I told you? This formula, remember this. This nu is equal to this omega is equal to gamma into B. So, or nu is equal to this long tail gamma into B. So, what will happen that now if I increase the B, this frequency will increase. Frequency will increase, the difference will increase. Fine. So, let's see how things can be changed. Yeah, like over here, like the way I've showed over here, that for this 42.6, and if I take this 13C at 4 Tesla now, it will become 4 times, like 10.7 something, 10.6 or 7, I just forgot. Yeah, 10.7. So it is 10.7. Fine. So it just increased by 4 times. You can see over here it become 42.8. It become almost equivalent to this. So yes, we can increase the sensitivity. We just increase the magnetic strength. But what happens that we can't do it on same instrument. Fine, that is the limitation. So always remember that the factor which will increase the sensitivity is not gamma, because it is constant, though different for different atom. So sensitivity will be increased by not gamma increment, but by magnetic strength increment. So the second term is like by amount, like by increasing the amount, can we increase the sensitivity? The answer is yes. Suppose there are 100 molecules of CH4. So 99 carbon are inactive, you know that. With that 12C1. So 13C, there is only 1% abundance almost. Right, over here 99% abundance is there. So almost one molecule is NMR active. So in that case, what will I do? If I take suppose 1000 molecule this time. Okay, I've taken 1000 molecule. So what will happen over here? 1000 molecules are there. So 1000, 1.1, this 1.1% of 1000 would be what? 1.1% would be 11. That is 13C abundance. 12C abundance is 98.9. So 98.9% of 1000 would be 989. So 989 molecules are inactive. And 1.1% of 1000 will be active. So that would be 1.1%. यार ऐसे करके देखो. कट गया, आ गया 11. Fine. So it would be 11. So it is 13 CH4. So these will be active. So these will be active. So now we have 11 molecules over here. So they can, 11 molecules now they can be excited and they can give signal now. But one limitation is we can't adjust more than this amount in our NMR tube. So our NMR tube, they are small and you can't adjust almost 20 to 25 milligram in 1 liter of tube like that. 1 ml, I guess. Yeah, of tube. Yeah, so you can't adjust more than that in that. So now going to the next thing again, quadrupolar and non-quadrupolar. I told you that spin number is 0, then it is inactive. If spin is not equal to 0, that is active. If I is equal to half, I told you this thing earlier, I is equal to half, that is non-quadrupolar nuclei. And examples are this. If I is greater than half, that is quadrupolar nuclei. Examples are this. Also, there is one more thing, that is non-quadrupolar nuclei always gives sharp signals. Remember that? Generally, sorry. So quadrupolar nuclei gives broad signal. We'll see exception to this also, that how non-quadrupolar nuclei is giving broad signal. Sometimes question come from there. So just stay with me till the end. You'll get to know what I'm saying over here. So you get sharp signal over here, and in this quadrupolar nuclei, you'll get broad signals. Fine. So let's see why it happens in this why does it happen that we get sharp signal in non-quadrupolar, and in I greater than half, that is quadrupolar, we get broad signals. So let's just come over here. Suppose there is one spin, I is equal to half. It is my spin is over here, and this is atom. So if I apply this magnetic field over here, so what will happen? Here attraction and repulsion will be balanced. But if I is greater than half, fine, so I is greater than half, so that means it will not be balanced. It will not be balanced. Sometimes it will be like this, sometimes it will not, it will be like this. So here attraction and repulsion between this ground state excited state, these are not balanced. So there will be uncertain energy levels over here when I is greater than half. Remember that I is equal to half, there will be certain energy levels, because this nuclei is feeling same spin over here. But if I is greater than half, these nuclei will not be facing same magnetic field over here, over everywhere. They would be uneven. So that means energy levels, they would be uncertain. So that means that is happening because attraction and repulsion by this, they are not balanced. Over here it is balanced. So if when I is greater than half, there will be uncertain energy levels like this. But if I is equal to half, like in first, in this case, there will be certain energy level and no uncertainty rule be followed here. No uncertainty rule will be followed over here. Remember that. In I is equal to half, in non-quadrupolar nuclei. Remember this is very easy deduction. If you did not understand, just listen to it. Just listen to the last 2 minutes and you'll understand everything. So in uncertain energy levels are there when I is greater than half. So Heisenberg uncertainty principle will be followed over there. So that means we can't find out del E and del T simultaneously. So always remember that. Fine. So the formula will be Heisenberg uncertainty principle, that is del E into del T is equal to h cut by 2 pi. If I just put this number, del E is equal to hc, this h nu, but h nu can be written by hc nu bar. Fine, that is over del is there, so hc del nu bar into del T, h will be cut. H cut means h by 2 pi, so it is h by 4 pi, it is del nu bar, it is 1 by 4 pi c del T. So what happens ahead, that if I is greater than half, over here we'll deduce something from here. So if I is greater than half, so let's say I is equal to 1, so energy levels will be 3. You can see energy level formula was 2I plus 1. So I have written over here there are 3 energy levels. So what is happening over here? Can you see there is less energy gap between these levels? When I is greater than half, that means I is equal to 1. So there are less energy gap over here. So that means there is less time difference between them. Yeah. So if time difference is less, okay. So over here you can see this del nu. Del nu bar is inversely proportional to del T. So del nu bar is inversely, so that means del nu is also proportional to del T, because nu and nu bar, they are directly proportional. So del nu is also inversely proportional to del T. So this will decrease, that is in uncertain energy level, del T decrease, because what happens, the time will be less between these two states. Fine. So this frequency difference, it will be more. So del nu will be more, so that means signal broadness will increase. So you will be telling me, Komal, del nu increase, so what is the thing over here that broadness will increase? Suppose you are getting signal over here and one over here, so the broadness will increase like this. Fine. So that is the thing with it. But if del nu is less, so like over here del nu is less, you will be getting signal like this, very close, and the signal will be sharp. Fine. Yeah, so the factors which introduces the broadness in any signal. Here you will be seeing that some quadrupolar nuclei. That's why I told you generally. That is I is equal to half. They should give sharp signal, but they will also give broad. So there are some example I'll tell you over here. So the factor which introduces the broadness in signal, that is called EFG. Why does it happen that some signals which are supposed to be sharp, they becomes broad? The reason is electric field gradient. Let's study it, that what is electric field gradient. Suppose there is ammonia NH3. The structure is this: 14N 14N I is equal to 1 over here, and it is 99.7% abundant. 15N I is equal to half, fine, it is 0.37%. Clear? So here non-quadrupolar nuclei will show broad signal instead of sharp signal. Let's see how. So what happens over here, if we go at the structure of ammonia, this you can see there is this spin, this proton nuclei over here of nitrogen. This will be remain very much bonded to its lone pair. This will remain very much bonded to its lone pair, due to which it will spend this nuclei, it will spend maximum time over here, due to which what will happen, it will feel the less external magnetic field. When you will put ammonia in external magnetic field, this nuclei will feel less magnetic field. So what will happen here, it is spending more time, so less magnetic field will be felt over here, but the moment it's come down over here, more magnetic field will be felt over here. So what will be happen, so it is due to axial symmetry over here, axial symmetry of NH3, unevenness will come. So there will be uncertain energy level, attraction, there will be not balanced magnetic field will be felt by this spin. So there will be uncertain energy levels. So we know that in uncertain energy level, del T decrease. In last slide I told you time taken between energy level will be less. So if del T decrease, so this nu is directly inversely proportional to this nu will increase. So if difference of if del nu increase, so that means you'll get broad signal. So here instead of 15N, I is equal to half. That means this is quadrupolar nuclei, but still we are getting broad signal. This is exception. So whenever axial symmetry is there, it will happen. So remember that. There is one more example. I think I have explained that way only. Okay, so there is one more thing, that what can happen, that what can we do, that okay, here we are getting broad signal because of axial symmetry of NH3, this spin is creating problem over here. What if I remove this spin only? Like what if I remove this lone pair is creating problem. What if I just remove this lone pair only? Then what will happen? Then what will happen? This will happen. See? Yeah, if we add H plus, if we add H plus to NH3, it will become NH4 plus, 15 NH4 plus. So that means if I just put this now, this spin in external magnetic field, it will feel equal magnetic field over everywhere. So that means now I'll be having certain energy levels. So that means I'll be getting very sharp signal. So now spin will feel, you can see it's written over here, they will feel equal magnetic field equally everywhere and will change into certain energy levels, and hence will get sharp signals. So 15 NH3 will give broad signal, and 15 NH4 plus, the way we discussed over here, it will give sharp signal. NH3 molecule, it possesses axial symmetry and it will feel uneven magnetic field everywhere. I hope that is clear to you. And this is the last slide of our lecture, and this lecture just remained for too long, but it was worth it, I guess. And that's all our basics of organic spectroscopy. I hope it would be helpful, but just let's sum up with this last slide. So there's thing between this chlorate and this perchlorate. Fine. So which one will give sharp and which one will give broad signals? So let's just see at the structure first. Chlorate ion has this ClO minus, this double bonded O, and over here it is Cl 3 oxygen doubly bonded, and this O minus like this. Fine. So what happened in this? In this one, in chlorate ion, spin will feel uneven magnetic field. Fine. Spin will feel uneven magnetic field. So yeah, what will happen that yeah, it is quadrupolar nuclei. It is I greater than half, that is 5 by 2. It has somewhat 5 by 2, I guess. Yeah. So what will happen? Spin will feel uneven magnetic field over here, and it will give us broad signal. But in case of this chlorate ion, perchlorate ion, in this, what happened? It should also show this broad, because it also has spin quadrupolar only. It should give sharp only, but what will happen? It will give broad, because what happens that everywhere this lone pair is removed. Fine. And now this extra oxygen has taken place, and due to EFG, electric field gradient, it will face equal magnetic field everywhere. You can see it will face equal, and hence certain energy levels will be created. But in ClO -3 there is axial symmetry. You can see over here there is axial symmetry, and there will be broad signal, there will be broadness, and broadness increase to that extent that signal will not raise from the baseline. It will not raise from the baseline. You can see signal will appear like this. When ClO -4, it will be like this. Fine. It will be a little bit strong over, sharp over here, and it will be broad over here. So remember, this Cl is active, NMR active, but it is not sensitive. So that's why we'll see that its signal is not rising from the baseline. So remember that ClO -4 sharp, because of this equal magnetic field experience, but over here the spin experiences more time over here, and it spend less time over here, due to which it will feel unequal magnetic field, and it will give uncertain energy levels, and uncertain energy level will decrease the time, and time is inversely proportional to nu. So del t is decreasing, so del nu will increase, that means difference in signals will increase, so we'll get broad signals. Fine. So that is the final slide of the basics of organic spectroscopy. I hope, guys, it was helpful and you learned everything, and a lot of questions come from here, a lot of time, and you are just blank. But if you know these very small things, it will be very helpful. Let me tell you, just go through this lecture, not in like one go, maybe just try to cover it in 2 to 3 go, and just try to grab everything. The basic, I have covered almost everything. You'll not see things coming from here and there. Just go through it, and you'll be pretty much covering up the basics of organic spectroscopy. And tell me if you have any doubts. I'll be entertaining your doubts in the comment section. If you have any doubt, please leave your queries or doubts or your compliments in the Telegram group or in the comment section. I'll be more than happy to entertain you guys. And yeah, tell me, how was the experience after almost after 1 year? Did you like the lecture? What can be the suggestion from your side? What should I cover more? Did I lack anywhere? Or just suggestion, your honest opinions, and your doubts will be more than welcome in my comment section and in the Telegram group. I'll see all of you in the next one with the new part of it. That would be, we'll be starting number of signals, that how do we deduce number of signal. And my god, that lecture is going to be so interesting, because it is related to imagination, and we'll be playing with lot of structures like camphor, pinene, blah blah blah. So don't forget to tune in that lecture, and I'm gonna come with more bang. So I'll see all of you in the next one. Till then, bye, take care, and keep smiling. Bye bye.